Hello friends, hi, my name is Doc Mo, and today we're going to be doing the Stats for Noobs video. Now this is almost like a second part to the video that we did on the research interview, and I just thought there'd be too much content for one video, so we split it out over the two. But you should go ahead and watch that one first before you watch this one. I'll put a link over here as well so that you can click on that and go straight to the other video. Okay, so firstly I'd like to just say that this is a video for medics. It's not for statisticians, okay? It's not going to have advanced stats or anything like that. It's going to be working under the assumption that you know zilch and that we're going to give you enough knowledge, hopefully after this video, to be able to go ahead and be successful in the academic interviews for the AFP. And the other important thing to bear in mind is that for AFP and for the interviews, it's more important that you've got a firm understanding of the basic concepts than a really tenuous understanding of the more advanced concepts, okay? It's really important that your foundations are solid. Okay, so the point of stats, okay, in all of medicine, but also in the context of this AFP interview, is that you can interpret the numbers and translate that into a plain language sentence. We'll talk more about this translation process a little bit later on in the video. And then from that plain language sentence, you've got to be able to translate that into changes in your clinical practice. That's what evidence-based medicine is. And the reason why we need to be able to understand stats is so that we can convert those numbers into some meaningful sentences and then from there into changes in practice. Okay, so without further ado, the structure of today's talk is going to be as follows. We're going to first of all go over some of the key definitions that you need to be aware of. We'll take a break in the middle of that and then we'll convert 3 of the common definitions into plain English sentences, okay, so that we can better interpret and understand these statistics. And then we'll go on and continue with the definitions before very briefly talking about different types of analysis. Okay, so the first definition that we're going to cover is the p-value. Now the p-value is the probability of the observed result or one more extreme occurring when the null hypothesis is true. Okay, but what does this actually mean? So we're going to talk about what the null hypothesis means, because that's a definition in itself, and then we'll talk about what that p-value actually means in layman's terms. Okay, so let's take a really simple example, the one that everyone always uses. Say for example, I suspected that a coin was weighted and that one side was more likely to always flip up than the other side. Let's say it was heads. My null hypothesis is what I do not believe, okay? I suspect that that's wrong. Okay, so my null hypothesis in that circumstance would be that there is an equal probability of heads and tails landing face up. Okay, so it's what I don't believe. And then for the H1, which is the alternative hypothesis, it's what I suspect is true, but I need to confirm by doing a study. Okay, so for example, if it was a one-sided study, I could say that my alternative hypothesis H1 is that the probability of landing on heads is greater than the probability of landing on tails. Okay, so that's what the hypotheses are. Okay, so now let's go back to the p-value now that we know what those hypothesis definitions are. A p-value is a calculated statistic, okay? It is the output after you finish research. A lot of people think that the p-value is 0.05, and that's not really true, okay? That value of 0.05 is the arbitrary cutoff that we use to then say that if it's below that, it's statistically significant. Let's go back to that coin example. Let's say, for example, that I calculated that the probability of heads landing was 0.8, okay, and that the p-value for that statistic was 0.05. Let's just assume that. What we're saying with that statistic is that there is a 5% chance that bit comes from the p-value of 0.05. There is a 5% chance of heads landing 80% or more of the time, okay, and that bit comes from the probability being 0.8. Okay, so I hope that makes sense, but just bear in mind that the p-value is the calculated statistic, and if the p-value for the stat is less than 0.05 usually, okay, we then deem the result statistically significant, and then we can then go ahead and reject our null hypothesis. Okay, let's move on to the next definition, which is confidence intervals. These are slightly different. So these are a range of values. So they're not a single value, which is what the p-value is. It's a range of values. The official definition for a 95% confidence interval is that it is a range of values between which the population mean value will lie 95% of the time. That's all gobbledygook at the moment. So let's pick apart that definition. And in order to do that, I'm going to use an example. Bear with me though, okay? Let's say, for example, we wanted to do a study into people who've got diabetes. The number of people that have diabetes in the world is huge. We would never ever be able to include all of these patients into a study. That is our population. Now from that population, we derive a cohort, a smaller cohort than the entire population. When we do statistical analysis on this cohort, okay, we could be looking at a difference in HbA1c levels, we could be looking at the reduction in the relative risk of complications of diabetes occurring. It could be anything, okay? But ultimately, we're going to try to work out a statistic for that cohort, all right? That's called the sample point estimate mean, okay? And we've done that for that small group. However, that sample point estimate mean, okay, may not correspond to the actual population mean value for the entire population. Okay, so they might be only slightly off, but it's very unlikely that it's going to be exactly the same value. As a result, we can then use the confidence interval to define a range between which we're going to find for that huge population, all of the patients, we would expect to find the population mean value. So what we're saying is that if we did that small experiment, it could have thousands of patients, but it's still not all of the diabetic patients. If we did that small experiment, the population mean value for the whole population would lie between those two goalposts, which is the confidence interval, 95% of the time. It's important to bear in mind at this point, this is not the same as having a 95% chance of having the population mean occurring between the confidence interval. And it's really important to make sure that you don't confuse those definitions, okay? So it's important that you don't say, when you're defining confidence interval, that there is a 95% chance of the population mean occurring within those two goalposts, because it's not a 95% chance. Is that if you did that small study 100 times, 95% of the time, the population mean value would lie within the confidence interval. If you'd like to know further why that's the case, you can go and look up the maths behind it, but I'm not going to explain it in this video because, to be honest, I don't understand it. Okay, so we've covered p-values and we've covered confidence intervals. We're going to start to pick up the pace now a little bit. So the next definition we're going to talk about is relative risk. Now, in medicine and in statistics generally speaking, risk is defined as the probability of developing an outcome. Okay, and in medicine, usually we say we're talking about developing a disease. Therefore, the definition of relative risk is the risk of developing a disease or an outcome for that matter in one group compared to the risk of developing that same disease or outcome in another group. Okay, it is the risk, which is the probability of an event occurring, and it is relative, so you compare the two. Suppose we had this table over here, where on the top we've got two columns, patients who got the disease and people who didn't get the disease at the end of the study, and then going down we've got people who were exposed to a risk factor and people who weren't exposed to a risk factor. We can populate the boxes with A, B, C and D, okay? You've got to be able to draw this table out, by the way, so I suggest that maybe you get a piece of paper and just jot this down as we go along, and we'll annotate it with some key bits of information in a moment. So the risk of getting the disease in the group that were exposed to our risk factor of interest is A over A plus B, okay? So A divided by, in brackets, A plus B. I hope that makes sense. And then the risk of developing the disease in the unexposed group would be C over C plus D. Okay, so we've got those two things. In order to now work out relative risk, all we need to do is do A over A plus B, and then that result, over C over C plus D. And that's it, that's your relative risk worked out. Okay, just a few notes about relative risk, because we'll talk about how you interpret it in just a few moments after we've made a couple of other key definitions. But just a couple of notes about relative risk. So the first thing is that generally speaking, you use relative risk for prospective studies. You cannot therefore use relative risk in case control studies. That's because case control studies are retrospective in nature, and if you haven't covered case control studies already, head over to my other video where I go on to explain case control studies a little bit more. Okay, now there's a mathematical reason for this, and I've included the reference in the description below if you're interested in that sort of thing. But again, we're not going to cover this in detail in this video. You should only use this statistic, therefore, like we said, in prospective studies. And the way that I remember this, unfortunately, it's quite grotesque, but as PR, okay? So prospective for relative risk, PR. The reason for this is that in order to work out this statistic, you need to be able to accurately determine exposure status and the outcome of interest, okay? And you can really only do this if your study is prospective. So now we're going to talk about odds ratio. This is where things start to get messy, and this is where things start to get a little bit confusing. But we're going to slow it down and just bear with me, and hopefully by the end of it, it will make sense. So odds ratio is very simply defined as the ratio of odds occurring between two groups. So in medicine, generally speaking, odds ratio refers to the odds of exposure to a risk factor of interest in patients who do have the disease compared to odds of exposure to the same risk factor but in patients without the disease. Therefore, next logical conclusion that we can make about odds ratio is that we use it usually for case control studies. So we use it for the studies that look back, that are retrospective in nature. So these are the studies, remember, where we've started off with those who've got the disease, and we've also got some controls, and then we look back to see if they were exposed to a factor of interest. So from a mathematical point of view, instead of it being A over A plus B, we're actually going to be doing A divided by C, okay? Because in the disease group, so this column going down here, you've got the odds of exposure to the risk factor are A to C. So it's just odds. And then you do B to D, and then you compare those two. So then you do the top one, which is A over C, divided by the bottom one, which is B over D. Okay, now from a mathematical point of view, okay, if the disease is really rare, odds ratio and relative risk actually end up being quite similar. However, they are not the same thing, and most times they can end up being very different. So you can't say that odds ratio is similar to relative risk. But ultimately, the thing to bear in mind is that the odds ratio, you use it for case control studies which are retrospective in nature. Okay, so we've covered relative risk first, where we said that that was for prospective cohort studies. And then we've now covered odds ratio, which is for the retrospective case control studies. Finally, we're going to talk about hazard ratio, and then we're done, okay? We're going to move on from these annoying definitions. Okay, so for hazard ratio, it gets even more confusing because actually it is quite similar to relative risk. Okay, so it was actually defined, I think, in the BMJ, but I'll include the reference down below in the description. It was defined as being broadly equivalent to relative risk, useful when the risk is not constant with respect to time. Okay, so it uses data from different time points, okay, where the risk might be changing over a period of time. Usually hazard ratio is used in the context of survival, but in statistics, survival doesn't just mean life or death. It could be whether or not a patient got a disease or not. It could be whether or not a patient survived without cancer or not. Okay, so we don't just mean life or death in this context. So there's an awesome paper which covers this, and I'm going to include this in the description below as well if you want to go further into this. But essentially, the thing to remember is that hazard ratio takes into account the principle of time, okay, whereas relative risk doesn't. So relative risk only looks at whether or not an event has occurred during the study, whereas hazard ratio takes into account, one, whether or not an event has occurred, and two, when that event occurred during the study. That's how it's simplified down. That's how I like to think about it. And if you want to go more in detail, you can check out the paper below. Before we move on though, I just want to go back to this diagram over here, and I want to re-highlight the fact that these stats mean absolutely nothing unless we can convert them into a plain language summary sentence, and then from that use that to inform our clinical practice and make decisions based on that. So what we're going to do here in this section is we're going to take those three definitions, relative risk, odds ratio and hazard ratio, and we're going to convert them into sentences using examples. In all of these examples, we're going to assume that the p-value is less than 0.05, i.e. for all of these examples, the result is statistically significant. Let's start off with relative risk. So let's say that the statistic was relative risk is 1.45, and that it was a prospective study which looked at two groups. One of them drank coffee, one of them didn't, okay? And we were looking at the outcome of interest being tachycardia, okay? We'll just use that as an example. So the relative risk is 1.45. The way that we would interpret this statistic is that in the group where patients drank coffee, they were 45% more likely to have tachycardia. Or we can also say that the probability of having tachycardia was 45% higher in the group that drank coffee. That's how we translate that statistic. It's really straightforward. We could alternatively say that in the group who drank coffee, they were 1.45 times more likely to have tachycardia, but that doesn't really make sense. That's not something that a patient would appreciate because it's not an easy way to interpret the data. If the relative risk was 5.1, it would probably be easier to interpret the data as patients in the group who drank coffee were 5 times more likely to have tachycardia than those who didn't drink coffee. Because the relative risk is higher, it's just easier at that point to swap from the percentage to the number of times more likely. So just use common sense when you're interpreting the statistic to convert it into a plain language summary. Okay, now let's do odds ratio. Let's say, for example, I did a case control study where I wanted to look at exposure to risk factors in patients that had oral cancer. Okay, let's say one of the risk factors of interest was chewing tobacco. Remember, with the case control studies, we start with the cases, so those who've got oral cancer in this circumstance, and then we take controls, and then we look at whether they were exposed or not to the risk factor. Let's say, for example, that the odds was 1.6. The way that I would convert that into a plain language sentence would be that those who had oral cancer, the odds of them chewing tobacco were 1.6 times higher than those who didn't have oral cancer. Okay? Notice the emphasis is on, I've used the words odds. I did not say that the risk of them chewing tobacco was 1.6 times higher. I did not say that those who had been chewing tobacco were 1.6 times more likely to have developed oral cancer. What I said was that the odds of chewing tobacco in the group who had oral cancer was 1.6 times higher than the odds of chewing tobacco in those who didn't have oral cancer. Okay, so make sure you use the word odds in this circumstance and not probability or risk. Okay, just one more thing to note at this point. An odds ratio of 1 indicates that there's no difference, okay? Because it's a ratio. It means that the two groups are the same. Similarly, a relative risk of 1 also means that there's no difference between two groups. And the same can be said for hazard ratio as well. So now let's talk about hazard ratio. Let's say, for example, I was doing a randomized control trial and I was looking to compare recurrence of cancer following use of a new drug, okay, a new chemotherapy drug. Let's say that the hazard ratio came out at 0.79. How would I interpret that statistic? So what I would say, and it is quite similar, quite admittedly, to relative risk, what I would say is that those who received the chemotherapy drug at any point during this study were 21% less likely to have cancer recurrence. That's how I would interpret the statistic. Remember, hazard ratio is quite similar to relative risk, but it's taking into account the time in the study. And once again, remember that hazard ratio of 1 means that there's no difference. Okay, that's all the really messy stuff. That's all dealt with now, I promise you. So we're now moving on to the relatively more straightforward stuff. So let's go through some quickfire definitions. Okay, so incidence is the number of new cases of a disease in a given time period. That's the first thing. So again, it takes into account the element of time. Prevalence is just the number of people who have a disease at a given point in time. Absolute risk reduction is the difference between the incidence of disease in one group, so that's within a given period of time, compared to the incidence of disease in another group. And quite simply, all you do is subtract one number from the other. It's as simple as that. Number needed to treat is 1 divided by the absolute risk reduction. And this is quite a useful statistic because it tells you how many people need to be treated with that drug, with that surgery, with that intervention in order to prevent one outcome occurring. And this statistic is quite useful in health economics because we use it to justify the introduction of new therapies based on how much they cost. So if something is relatively non-expensive and you don't actually need to treat a lot of people in order to prevent one outcome occurring, then actually you would introduce that thing quite quickly. Relative risk reduction is the absolute risk reduction divided by the control. So it's a percentage. So that's all it is. So all you do is you get the absolute risk reduction and you do it divided by the control and then you express it as a percentage. Okay, let's quickly talk about error. So the key things that you need to know about error are type 1 and type 2 error. Okay, so type 1 error is where you falsely conclude that there is a difference between two groups when in actual fact there is no difference, i.e. the STATSI definition is that you conclude that there is significance, okay, in your findings when actually H0, so your null hypothesis, is true. What this means from a practical point of view is, say you did a study and you determined that P is 0.03, so then you said, oh, this new cancer treatment is better, it prolongs lives, yada, yada, yada. In actual fact, it doesn't, but your study has demonstrated that it has. Usually we accept that there's a 5% chance of this happening, and that's why statistical significance is usually set at when P is below 0.05. Okay, and then if we just summarize that in 2 words, it's basically just a false positive. This is in contrast to a type 2 error, which is a false negative. Okay, sometimes you'll see beta thrown around. So beta is the probability of making a type 2 error. Usually we say that if it's under 0.8, we're not too fast. Above this, and you've got to start thinking about the quality of your study. Okay, and this moves us on nicely, finally, and I promise this is our final definition, okay? Onto the definition of power. Now, power is the ability to pick up a difference when a difference exists, i.e. it's the probability of not making a type 2 error. I know that can be quite confusing, so if you want, pause the video at this point, go back to our definition of type 2 error, and then try to work out why that sentence makes sense. Okay, and there are three main ways that you can increase power really. You can either increase the sample size, you can increase the effect size, or you can increase the precision with which you measure the outcome of interest. Okay, phew, so that's all done. Now I know I promised that there's no more definitions, but there's just two more concepts that we need to cover, so they're not strictly speaking definitions, and so we're not breaking any promises here technically. So the first type of analysis that we often encounter in medical statistics is per protocol analysis. Now what this is where you include patients in analysis within the study only if they've finished doing the study protocol properly. Now this has got some advantages and it's also got some disadvantages. The advantages is that we're getting an accurate representation of the effect of the intervention, okay? Because you've included only those people that properly did the intervention. So whether that's they stuck to the drug dosing, they managed to complete the physiotherapy exercise program, whatever it is, the patients have completed it successfully and then been included in analysis. Obviously, the disadvantages of this is that it's susceptible to attrition bias as well as exclusion bias. And that's where the intention to treat analysis kind of comes in and complements it. It's almost in contrast to per protocol analysis. So intention to treat analysis is basically where you usually include all the patients who've at least kind of attempted to have the intervention. So it could be patients that started taking the new drug and then didn't take it for the rest of the study, or patients who kind of took the drug but not as consistently as you wanted to. So it's patients that would have started on the study and usually had 1 or 2 doses of the drug. So have a look in the abstract, and if you can't find it in the abstract, have a look in the main paper to see what the criteria was and which method of analysis the paper did. Obviously, the advantages of intention to treat is that it's more accurate of results in clinical practice, because in practice, patients don't always take their meds, patients don't always stick to the plan by the book, and intention to treat analysis more accurately reflects this. Obviously, on the other hand, and it's obviously the complete opposite of per protocol analysis, you're not getting a true accurate estimate of how well the drug actually does in optimal conditions. Okay, thank you very much for watching this video. I hope you found it useful. If there's something that I've missed out, feel free to pop it in the comments below. Check out the other videos in this series as well, and all the best with your AFP application. Until next time. Phew.